of stuck with what to do from an architecture point of view to actually help the situation substantially, because all the papers that we've read say that like basically the structure we have is pretty good, and the one we're reading part one for power. And this course has been geared so much toward speed, but well, now what?
Yeah.
So, and what's worse, I spent most of my time in phase 2 focusing on like circuit level stuff. And after all the analysis and doing the circuit, it turns out it's just slightly worse. So,
What are you doing here? I gotta cut you on. Oh. It's gonna be quite exciting. Need to brush up on my 141 material? Yeah. Hey, I'll mind ask you some questions, and if you don't, you might have graduated and answer them. I think I'm gonna take off then.
Right. Maybe a good idea. All right, here we go. You want a signature too?
No, not today.
Not today, yeah?
You can read it first.
Good, alrighty. Sounds good. Great, thanks.
Not completely, but close.
is your final draft, or are you?
It's pretty close. There's some of the introduction is not the first few paragraphs are some of the stuff, and the conclusions are kind of just another paragraph. All the content's pretty much there.
Anything this semester or next?
Definitely this semester.
Yeah, for just a little bit of extra notes in the summer. Yeah, it's a question of weeks, not years.
Yeah, definitely. It's not that far away. Yeah, the guy can make it, but got that ask down there.
Yeah.
You're like, does the rest with me anymore?
Okay. You should. Wake up.
James, are you free tomorrow after class? Sure.
You're happy. Alt Control down. Just gonna take a little bit. Computer is on an off day. Doesn't want to work on Tuesdays.
So, but for the larger stuff, that'll basically amount to doing like a
Getting there. Rebooting the computer. Almost there. It was in an unknown state. Alrighty, good afternoon. So these are the real diehards. Anyhow, good. A couple of things about the project. Let me just make sure that I get this out of the way. Let me put this somewhere on the side. Close message. Good. So regarding the project. We have sent out a number of emails already. There's a couple of them more that have to be sent out, so if you haven't gotten anything yet, don't worry about it. It will be there by tonight, early tomorrow morning. As I mentioned before, this is an interim report, so what we're giving you is some feedback, like, hey, this is the right direction, keep on pushing, or maybe you might reconsider this a little bit here and there. But overall, I think people got in general, I think people did. There's two possible ways of attacking the problem, and I've seen both. So I've seen most projects have done kind of combined effort at the logical or at the topological level, restructuring the thing in such a way that you minimize the overhead or minimize the logical depth. And the other one is working at the circuit level. What circuit structures to take, what type of adders to use. I've seen every possible answer in the overall picture. People have gone from mentioned carry chain to look-ahead structures to carry select adders to carry bypass structures. So we have the whole grouping of things. So it's going to be interesting. I'll put it all together. Now, tomorrow lecture, for those of you who are watching or are delayed watching the lecture, it's important that you attend tomorrow's lecture because that's when I'm going to have the sign-up time for the poster sessions. Yesterday, I posted the kind of detailed instructions on how you should compose your poster, what the material we would like to see, what the type of things you have to do by then. Your poster is going to be your final report as well, so I'm going to expect actually an electronic submission of it to keep a hold of. So the way it works is you will get like half, we kind of group by half hour or hour slots. And you sign up for an hour slot. You have to make sure you're there on Wednesday afternoon. It's going to be probably between 1 and 5-ish next Wednesday. Going to have a continuing poster session. You get about 10 minutes. Or for time, that's not much. So use it efficiently. Definitely the fact that out of that 10 minutes, we're probably going to use about 2 to 3 minutes to ask questions. So you have about 7 minutes. And it's going to be a lesson in how to efficiently convey key messages. It's like the same thing like you want to start a company and you go to a venture capitalist somewhere on Sand Hill Road in Palo Alto, and you want to ask them for $10 million. They give you 5 minutes, and you have to convince them in 5 minutes. So that's all you get. You don't get 2 hours with 500 PowerPoint slides. No, you get 5 minutes to explain them why they should give you $10 million. So that's kind of the same idea. You have 7 minutes to explain why your design is really, really cool. Okay? So so we're going to circulate the sign-up sheet tomorrow in the lecture. So it's important that if you want to get a good slot or the preferred slot, either early or late, depending on if you're ready or not. You definitely have the first chance when you're here in class. Okay, let me do that. All right, so that's that. Any other questions regarding projects or any other things? This thing should be quiet, so I'm going to move it off the side. There we go. I just solved problems. Any other questions, concerns? Okay, if not, so what we'll do today is continue about discussion of interconnect. So what we've done so far is discuss capacitance. Yes?
For the register, are we going to have to do the layout for the register, or
no?
No.
No. Didn't you get? Did you? There is there's a layout for the register, isn't there? So I will check right away. I thought there was a layout for the register that you could use, and that's the one you should basically stick to. If not, okay. No, you don't have to do it. It's really focus on the adder array, make it as efficient. But so obviously it becomes a little bit more tricky if you start, as a lot of you have done, is interchanging registers and adders and so on and so forth. So they have to kind of match together. They have to kind of fit together. So you need a design for register. So let me check right away, because I assumed there was a layout for the register and that you wouldn't have to do that. Okay? Good. So we've done talked a little bit about resistance. We talked about capacitance, and we started a little bit about talking about inductance. Why inductance is important. So I'm going to wrap that up first, and then we're going to talk about how you deal with some of those effects. What do we do with large capacitive wires? How do we deal with resistance? How do we deal with inductance? That's kind of the idea of interconnect design, right? And then there's two special cases of interconnect design that deserve special attention. That's the clock network and that's the power network. Because the clock network obviously is a network. It's very important from a skew perspective. It's also very important from a power perspective. The power distribution network takes a lot of current. And if you don't design it carefully, it might ruin your design. So bringing lots of current into a chip is not a trivial thing. So that's kind of the scope for the next two lectures, today's and tomorrow's. Alrighty. So let's go back to inductance. So if you look at the wire, and we really start looking at the higher speeds. High speeds, and at the same time, signals with fast transition times. Okay? We see that the wire now becomes not only resistors and capacitors, but also has inductance coil. And if you model this carefully, we see that now this becomes a wave and transmission line. A transmission line, like you've seen in EE117, is the area where we discuss this type of things. So what's really happening is that if I apply a step here, it won't basically propagate right away, or it won't diffuse like network, where you really have the waveform, the steps gradually but surely kind of diffusing the line. Now in this case, it's going to become a wave. This wave, it's a waveform that's going to propagate from one side to the other side, just like light does, or radio waves do. And when it reaches the end, there might be something happening there. The wave comes at the end of the wire, and depending on what's hanging off there, it might be either reflected or absorbed. Just like if I shine light on the surface, you get a certain level of reflection and absorption. Right? So there's an electromagnetic wave, shuffling really charge, or basically energy from capacitance to inductor, capacitance to inductance, capacitance to inductance. That's the way it works. This is obviously assuming that there's no resistance. I assume that the resistance is quite small right now. Resistance is just going to add loss to this whole process. So we mentioned at the end of last class that the wave propagates with a certain speed, which is determined by the speed of light. And for silicon, it's about 15 centimeters per nanosecond. And the inverse of that is the time of flight. It's the time it takes from this waveform to propagate from the start of the line to the end of the line. And the final property is the characteristic impedance of a wire, Z0, which is a real value. and which is given by the square root out of L over C, where L is the inductance per unit length, and C is the capacitance per unit length. Okay? That's where we are. So let's see what's happening here. So as I mentioned, depending on how you terminate the wire, many different things can happen. If I have an open circuit, so I have a wire and I connect nothing at all, a incoming wave will arrive at the end and be totally reflected. So if I get a waveform coming in with a voltage V, it reaches the end, it gets reflected, you get a second waveform going back, the value on your wire will become 2V. Okay, because now you have your incoming waveform that sets the whole thing to V, slowly but surely, and then you have a waveform coming back, adding another V to it. Now, if you have a short circuit, it's just the opposite happens. The first wave comes in at a value V, reaches the end of the transmission line where it gets short-circuited. It means it's 0. So the 0 now is going to propagate backwards by basically having an inverted waveform. If the waveform coming in had an amplitude V, the waveform or the step going back is going to be minus V. The sum of the two becomes 0. The whole wire is going to be set to 0. We finally see that at the end of the wire is short circuit. If, on the other hand, we terminate the wire with Z0, the characteristic impedance of that same wire, what's going to happen is the waveform comes in and nothing comes back. It's done. It's finished in one shot. Okay? Now, the way we can characterize this is by defining what we call reflection coefficients. At the end of the wire, the reflection coefficient is 0. Nothing gets reflected. In the case of a open circuit, it's rho is equal to 1. We get complete reflection. And in the case of a short circuit, we get minus 1 reflection, which means that the inverted waveform gets reflected. And rho is nothing else than the ratio of the reflected voltage over the incoming voltage, or the incoming reflected current over the incoming current. And is given by the following expression. R is the resistance of the termination, the resistance seen at the end of the wire. So you can see that if R is equal to Z0, rho becomes equal to 0. If R is equal to infinity, you get infinity over infinity is equal to 1. If, on the other hand, R is equal to 0, you get minus Z0 plus Z0 is minus 1. And it can be anything in between. Right? So let's look at it a little bit more in detail. So here's an example of a wire which has a load resistance which is equal to infinity. Okay, at the end of the wire, we have an open circuit. Now, so you have basically the following situation. You have an incoming waveform, a step, let's say. The step has a source resistance to it. Right? Every voltage source has a certain resistance to it we call RS. Then you have your transmission line, and then at the end, there's nothing. It's an open circuit. So that's really the circuit we're studying here. A step, an ideal voltage step, a source resistance RS, transmission line, open circuit at the end. Okay? Now, let's see what's happening. Suppose that RS is equal to Z0. Let's take the middle case. Okay? So we choose RS so that it's matched to the impedance of the transmission line. We apply the step. If you look at the wave coming in, the voltage step looking into the transmission line, what you see is an impedance equal to Z0. You look at it, the waveform comes in at sees Z0. So it means that initially what you're going to get, the injected waveform is going to be RS over Z0. Right? So I have a voltage step, and I have a resistance which is equal to RS, and then you see going into the line an impedance equal to Z0. So what's the voltage that I will see when I now start applying the step? There's no capacitance here. What's the immediate voltage that I will see at the beginning of the transmission line? Do you know what it's going to be? You have RS is equal to Z0. This is Z0. What do we get? 1/2. Exactly. So we apply step V. Let's say V is 5 volt. The first step we're going to apply, you right away see the black is the voltage at the source. So it's going to go right away to 2.5 volt. Now, by the way, this is the the voltage, what this shows is the start and the end, and this is time. Okay? So this waveform now starts to propagate. You said you get a voltage injected in the transmission line equal to 2.5 volt. It propagates to the end. What's happening there? It's an open circuit. What would you expect? It's going to reflect. Right? So at the end of the waveform, you see the red line. That's initially 0. One time of flight later, the waveform arrives at the end of the wire. 2.5 volt. But remember, you right away get a fully reflected waveform of the same value. So you get 2.5 plus 2.5, you go to 5 volt. And bingo, we're done. Because what's going to happen now is this waveform gets reflected backwards. So you have 2.5 volts, 5 volt, and this 5 volt now goes all the way to the beginning, and they become the same as the source. So finally, after 2 times of flight, the source is also at the beginning here, this voltage here is also at 5 volt, and we're done. So you can see that when I use termination, when I terminate the transmission line with an impedance equal to Z0, the time it takes for us to settle is quite short. Now let's look at another case. Let's assume that I make RS very large. Okay? I make RS equal to 5 times Z0. Okay, so what is going to be my initial voltage that I'm going to inject? You have a RS equal to 5 times Z0. So let me erase that. Eraser. So what I'm going to get is now something of this nature. So you have RS, and you have here Z0. Z0, 5 times Z0. That's what I see at the source end of the transmission line. So the voltage, when I apply a voltage V here, the voltage I'm going to get here is what? That's just a resistor divider, is Z0 over 5 times Z0 plus Z0 is 5/6. Sorry, it's 1/6. 1/6 of V. And indeed, that's what you see. 1/6 of 5 volt is 0.8 volt approximately. So let's take a step. Step propagates to the end, gets there, gets reflected, which means it doubles its value. Okay, we double the value very nicely. It goes back to the source. Okay, it goes back, travels back to the source. If you now would compute the reflection coefficient at the source. Now the waveform goes to the end, gets reflected completely, right? You have an open circuit. It travels back. Now what's going to happen at the source really is determined by the reflection coefficient. So the reflection coefficient, remember that's R minus Z0 over R plus Z0. I think that is correct. Let me just check 100%. Yeah. So if R is equal to 5 times Z0, what we get is 4 over 5 times Z0 over 6 is 2/3. Right? So it doesn't get a complete reflection, but it's a certain fraction of it. So we can see, but it's still positive too. It means that we get back at the source, like this waveform gets back, we have this voltage, we get another step upwards. This goes from the source back to the end. Again, we get an extra step upwards, which is a complete reflection. There you conflict, and so on and so forth. And you see, gradually but surely, this waveform slushes back and forth from source to end, source to end, source to end, end to source. Till finally, after a long time, it goes to its final value. Now you can see that's a slow process, right? This is going to take, your time of flight is a time that's the minimum speed it can basically, the absolute fastest circuit I could get, right? You cannot go faster than light. At least not that I know of, or you have to have some quantum entanglement or something like that, which I haven't seen used in circuits yet. So here we see that it takes about 10, 15 times of time of flight for the circuit really to reach its final value. So that's not a good idea. So let's look at the other extreme. Let's look at the extreme that I make my source resistance very small. Actually, I use Z0 over 5. So it's a tiny resistor here. Instead of a big resistor, this now becomes Z0 over 5. If you compute this reflection coefficient here, you will see it's negative, right? Z0 over 5 minus Z0 over Z0 over 5 plus Z0 is going to be approximately equal to minus 2/3. I think it's minus 2/3. Which means that the waveform, when it comes back at the source, will get reflected but actually inverted as well. So now we get the very interesting thing. Let's look at what's happening. Step 1, we inject the waveform. We get Z0 over 5 over Z0. It means that the voltage we see instantaneously at the beginning is almost going to be 5 volt. Right? It's going to be, again, our resistive divider. It's Z0 over 5. Sorry, Z0 over Z0 over 5 plus Z0. It's about 5/6 of the value, which means almost a complete value V. So our input, our waveform almost goes right away to 5 volt, 4 point something. It travels to the end, open circuit. Right? Open circuit means complete reflection. So we get 4 volt, it gets doubled. It goes to almost, it goes to 8 volt, overshoots. That waveform travels back, gets at the source. There we'll see a negative reflection. Right? It's going to invert itself. So you have a waveform coming back of 4 volt, and now it's going to get turned around, so you subtract it again. That's why our waveform basically will go the other way. And as a result of this, because of the positive, negative, positive, negative, positive, negative factors, what we see, we'll have a waveform that goes up and down and up and down and up and down. It overshoots, undershoots, overshoots, undershoots. And finally reaches its value. Again, this takes many times of flight. It's a slow process. So if you look at it, the ideal way to basically drive a transmission line, if you know it's going to be transmission line behavior, is to make sure that you either match at the source or at the end with the characteristic impedance, Z0. If you do that, your waveform comes in and bingo, gets absorbed, and you're done. So that's the fastest possible process. Now, this used to be only a problem on boards. Right? You think about boards, you have very nice thick metal wires, copper most of the time, good dielectrics. So if you start seeing, if people start doing, let's say, memory system design, you have a memory bank processor, and you have to go really fast from your processor to your memory bank. This was clearly pure transmission line behavior. Almost no loss. The resistance was very small because you have thick copper wires. So transmission lines was very important in these cases, and you always have to terminate it with resistors equal to Z0. Otherwise, it's going to be very slow. If you look at things like SDRAM, for instance, the synchronous DRAM that you all use now in your computers and the really fast device, that's all SDRAM these days, zippingly fast bus that goes off the chip. And again, if you want to make this thing work, you have to terminate it. If you don't terminate it correctly, your SDRAM won't work at all. So these things are not easy to use. You have to look very carefully at your traces on the board, and you have to do the right type of terminations. Now, if you go through, let's say, you go to on-chip. In the past, aluminum, thin wires, not much of an issue. However, you have long wires on a chip that are thick copper wires, very small resistance, so no loss factor, sharp wave edges. With the technologies today, we can actually have waveforms that go up in a couple of picoseconds, or let's say tens of picoseconds, very fast transitions. There, again, transmission line effect starts to play. You have to start thinking about using these things on the chip as well. Okay, so that's something to remember. Every time, however, every time you look at a waveform and you see this thing happening, you know that you're basically dealing with some transmission line reflections. Very often, oscilloscope, you measure something with an oscilloscope and you see, you get a very wiggly waveform and you think, boy, my waveform is bad. Be careful. It might be that your probe itself is not terminated very well, and that the wiggly effect is the cable going to oscilloscope, definitely at very high speeds. So make sure that probes that you use to measure signals are also well terminated. Otherwise, you might get the old wiggly effect. But it could be the chip itself too, obviously. Now, Analyzing those things is complex. And if you ever would have to analyze it by hand, so how would the waveform basically propagate to the thing? This is what I recommend here. It's called the lattice diagram. It's a very simple way of evaluating how a wave propagates from one end to the other one and basically settles out. This is exactly the same example as the first one I showed. This is this example here, the top one. Rs is equal to 5 times Z0. So Rs is 5 times Z0. RL is infinity. So rho S is equal to 2/3. Rho L at load factor is equal to 1. Complete reflection. So as we mentioned, the first signal, if you apply 5 volts, the first signal we're going to inject is 5 volt times Z0 over 6 times Z0. That's 5/6 of a volt is 0.833. So this is the source end now. This is destination. This is the time it takes to go from one side to the other one. It's L over V is equal to the time of flight. So the waveform comes in, and here we have time. So we start with basically injecting a waveform of 0.833 volts in the transmission line. It propagates to the other side. So we have a waveform plus 0.833 propagating from left to the right. When it arrives at the right, we get a reflected waveform equal to the same value because rho is equal to 1. So we have an incoming waveform of 0.833 and a reflected waveform of 0.833. The sum of the two is 1.66. Right? So we double, 0.833 comes in, reflected waveform gets added, they double to 1.66. This waveform travels back to the beginning, arrives here. We had originally 0.833 as a voltage. 0.833 gets added, but then we reflect 2/3 of it. So 2/3 of this is 0.556. So you combine this voltage, 0.833, with the incoming waveform of 0.833 and the reflected waveform of 0.5556, I get 2.22. So that's the voltage after 2 times of flights at the source. Again, this thing travels to the other side, gets reflected completely. So you have another reflected waveform of 0.566 or whatever. The voltage here is going to be 1.6 plus 0.5 plus 0.5 is 2.7. And you keep on doing this back and forth, and you find all those values. So it's a very simple way for you to evaluate how this thing operates, or basically how the voltages evolve over transmission line. Okay? Now, before I go to the rules of thumb, well, actually, let's do the rules of thumb first. So now you have to ask yourself, when do I have to worry about this? Right? One is the case that I have to consider. Obviously, there's 3 models, right? I can consider the wire purely as capacitive. I can consider the wires as an RC network. Or I can consider it as a transmission line. So for the rules of thumb are the following, to basically kind of simple. You should, first of all, obviously, if I would take a input signal that is very slow, let's say I have an input signal that rises, suppose my time of flight is what? Let's take a wire of 1 centimeter, approximately, let's say 10 nanoseconds, 10 picoseconds, sorry. 100. 1 nanoseconds divided by 10, it's 100 picoseconds. So time of flight of 100 picoseconds, 1 centimeter wire, approximately, on a chip. Okay? So my time of flight is 100 picoseconds. If I now would have a signal that I apply, let's say with a waveform that has a rise time of 2 nanoseconds, you're not going to worry too much about transmission line effects, right? Basically, waveform goes very slowly up. During that time, it's going to shuffle back and forth a couple of times, but that shuffling back and forth is so small compared to the rise and fall. So your rise and fall time should be shorter than 2.5 times t flight of your signal. Otherwise, you don't have to worry about it. Okay, that's rule 1. So transmission line effects only show when you have sharp edges, signals that basically change quite rapidly. Okay, that's 1. Number 2. If the resistance of the wire gets too big, the diffusion effect starts to dominate. you will see that the RC time constants will be much larger than your time of flight and will dominate. So in that case, I don't have to worry about transmission line effect either. I just model this as an RC wire. And the rule of thumb is that when R is larger than 5 times Z0 of the wire, we should basically, if R is smaller than 5 times Z0, then you should consider transmission line effect. If it's larger than that, it's just a diffused wire, an RC wire. Okay? And also, obviously, if the resistance is smaller than 5 times Z0, it means that the wire still has kind of a reasonable resistance connected to it, right? Say that Z0 is 50 ohm. Let's make it 100 ohm. 5 times Z0 is 500 ohm. If I use a thin copper wire, you will see that your resistance is going to be not ignorable. It might be a couple of hundred ohms, maybe 100, 200 ohms. It's smaller than 5 times Z0, so you will have transmission line effects, but still you will see a loss factor. In that case, we have what's called a lossy transmission line, where you have a combination of two factors. You have wave propagation, but at the same time you have an attenuation of the signal that propagates because of the RC effects. They play together. Doing this by hand is hard. Fortunately, SPICE has some good models for it. You can put the transmission line in there, it will do it nicely for you. If, however, R is smaller than Z0 to, let's say, 50 ohm approximately, then you can consider it's a pure LC line. That's only going to be the case if you have thick copper wires. Wires that are sitting on level metal wire 7, 6, 8, 9 or something like that. Okay? Now, if you have transmission lines, what should you do? What are the things that you have to play around with? As I said, you should think about termination. And here's some examples, but let's not worry about that. So there's two options. Let's think a very, very simple example. Suppose I have an inverter. Long wire, right here, transmission line, driving another inverter on the other side. Very typical case, right? You have a very fast, big buffer, huge wire, another buffer on the other side. If I make this thick copper, I have nice transition lines. Say this thing is a big driver, so the rise times and fall times are very short. What's going to happen? Well, if you look at it, this is a capacitive termination. Right? There's no resistance here. From all practical purposes, I may assume that this is almost like an infinite open circuit type of termination. Right? There's no current flowing in there. There's no resistance, or an infinite resistance. So in this case, we will have a full reflection. This is the case that rho is equal to 1. So if I want to fight transmission line effects, there's only one thing I can do. And that's what? What would I do? The termination at the end is determined, right? It's a capacitive termination. It's open circuit. I want to make sure that I don't have this waveform shuffling back and forth. What should I do? You could set the resistance where? At the source? Destination? That is one option. That's what very often is done on a board level solution. What I'm going to do is put a resistance here to, let's say, the voltage you want to get, which is equal to 50 ohm or 100 ohm, depending upon the trace. The problem with that approach is that in the end, you will drive continuous current. Right? So you have your driver, puts the waveform goes through, settles, and you will see current flowing continuously from the driver through the wire and the terminating resistance. That's a lot of power. So what's the other option I can do? So that basically would mean termination at the end, right? Load end termination by basically adding a resistance here from here, let's say, to ground. And again, this is something which is very often done. But from a power perspective, it's not what I would choose. So what's the other option? The one we showed actually in the example before. Is make the source resistance 50 ohm, right? If I go to this example here, if I make my source resistance, sorry, not this one. Here. If I set the source resistance to 50 ohm, like I do here, you can see that the waveform goes to the end, gets reflected. We have right away, after one time of flight, we reach the final value. And then one time of flight later, the source also goes to its final value. So if I make the sources, the resistance driving the wire, 50 ohm, or Z0, I have a very good response as well. So how would I do that? Well, actually, it's not that hard to do. If I look at my inverter here, oops. If I look at this inverter, that's the driving resistance. We know the resistance, right? It's the PMOS or the NMOS device. So what I have to do here, if I really want to get the fastest possible response, I'm going to size my NMOS or my PMOS in such a way that I get a resistance which is exactly equal to the characteristic impedance of the transmission line. So I'm finding my PMOS in such a way that it's 100 ohms or 50 ohms or whatever the transistor is. And I can easily do that because we know how to size transistors. So that's the way we most often will do it on chip. Off chip, people most often use the resistance approach, where you put a bunch of resistors next to you have a bus coming off the chip, you have your memory bank. Next to your memory bank, you will see a whole bank of resistors sitting there, very often. Okay, these are those 50 ohm devices, or 75 ohm, or 100 ohm, whatever it is. Okay, so that's important to remember. If you're really going to go into this very high-speed area, for instance, go work for a company like Rambus, you will learn those things. You will learn them very well, because this is the thing, this type of stuff that those people are struggling with continuously. You have to want to have very fast signals coming off on a chip or between different components of a system. That's what you worry about. Okay? Yes?
A question about the output resistance of first inverter. If we are trying to match the transmission line impedance, so that means we need to use a very big inverter for the driving.
That is correct.
Otherwise, we probably need to operate it in the trial region
yes.
to get a very low resistance.
Yes. So the thing is, I really my goal is to drive this wire as fast as possible. And you can say, well, I'm not going to worry about it. I'm going to make it resistive, the whole thing. But then you're going to be a lot slower in your time of flight. If you really worry about that time of flight, let's say I want to go to cache memory or a core memory of the processor thing. The time of flight, the time it takes to get the data back out of memory is extremely important. So you want to go as close as possible to F, the time of flight. And that's why people are willing to invest large resistors, or basically large transistors driving this thing, and really do the matching. Because that's the only way you get to the absolute fastest response. There's no way to get faster than that. If you basically at the speed of light, you're there. And you can get darn close, but you have to be very careful in how you size the wire. You want to make sure it's not resistive, and you have to match the impedances of the wire and basically the driver. Okay? So yeah, these are big, very big transistors, but you get something for it. It's speed. Okay, so now, so we have discussed all those parasitics: capacitive, resistive, inductive. Right? Wires add all those things to it. Now, why do we worry about it? Well, every time we have something added to a wire, like we basically do with a transistor, anytime we add parasitics, you're going to get some impact. And what interconnect parasitics mostly do is impact two things, very importantly. It impacts performance. That's obviously right. I have a wire with more capacitance, it's going to be slower. If I have a wire with resistance in there, it's going to be slower. If I add transmission, even if I have inductance, you have to be very careful. So it affects the performance, but it also affects the robustness. As we will show you in a minute, capacitors to neighboring wires or basically resistance of a wire, all of those can basically degrade the integrity of the signals you're transmitting, and as a result of that, your circuit might fail. So you have to be aware of those. You have to model them correctly. You have to include them in your analysis. Otherwise, you might run into some very unpleasant surprises. So when we were doing 1 micron design technologies, nobody worried very much about wires. Wires were kind of, but now with transistors getting faster and faster and faster, all those impacts of the wires have become more and more important. And that's why you have to pay attention to them, or you might be very unhappy. So here's, for instance, an example of how capacitance can impact performance, or basically robustness. A very simple case, cross-wire capacitance. Something already discussed. You basically start now stacking wires together, and all the wires are kind of these rectangular structures. And then you have dielectric, another set of wires on top of that. And we make those things kind of very skinny and very tall. The capacitance between those wires is going to be fairly large. So what could this do? For instance, here's an example. So suppose I have a domino node. Your traditional domino logic design. So this is a dynamic node. Very high impedance. Right? That's the idea of dynamic logic. There's no connection to VDD and ground when the node is floating. Suppose now that I have a neighboring wire that overlaps for a certain amount of time, or that runs parallel with your wire for a little bit. You might not even know, but you do that on the chip and you put the two wires parallel with each other for a while. You build parasitic capacitance. Really what I'm going to see here is now that you have your dynamic node has a capacitance Cy, and between my signal X, which is a neighboring signal, and my dynamic node, I can see that there's also going to be some interwire capacitance, CXY. Now, suppose I pre-charge this thing to 2.5 volts. Right? I pre-charge the wire, and then while this is pre-charged, a neighboring signal is actually going from 2.45 to 0. Okay? So the neighboring signal just is going to go to a transition. The dynamic node, let's say, is supposed to stay high. What we see is that you will get a capacitive coupling, and we know charge conservation. The voltage at this node is going to change, so we know that the voltage at this node is going to change as well. And the value, the change of value, delta Vy, is actually given right here, is equal to delta Vx over Cxy plus Cx plus Cxy. Now, if Cxy, the cross-coupling capacitance, is almost of the same size as Cy, right? If you run these wires kind of quite a bit with each other, you can see that half of your delta Vx might be coupled into that dynamic node. And you're toast. Your circuit is not going to work anymore. So neighboring wires, definitely if you have dynamic logic, if you have nodes that are high impedance, you better watch out. What you're going to do is be very careful in your layout and make sure that you don't cross signals like that together. You keep them apart from each other. Now, that's easier said than done because most of the wiring these days in modern chips is not by hand, but by basically computer tool. You have a router, something that basically puts all the wires down. So if you really want to do dynamic design and you want to use dynamic routers or basically CAD tools, you better be careful that you put the right constraints in the router that it doesn't violate my rules here. So that's why most people doing dynamic design very often are actually going to use basically hand routing. Very carefully place the wires, take them apart in such a way that you don't violate those rules. Okay? So that's an example. Now, this for dynamic nodes, so that's okay. Maybe I'm only going to do static design. Right? That's your full right to say if I avoid static node, these dynamic nodes, I shouldn't have a problem. Well, you still can have a problem because here's now the same case. Well, it's a similar case. You have two nodes, X and Y. X is what I call a violator, or basically somebody that kind of is a neighboring signal. Y is a signal I care about. Okay? Now, suppose now that I have a 0 at node Y. Okay? It's driven by a voltage, so it's a static node. You can see it's either driven to ground or to VDD, as we want to see in any static design. Right? Now, a neighboring signal is going to go to a transition. Okay? Now, obviously, again, you will see an impact. We still have, again, a capacitive divider. You have an instantaneous effect. This thing goes up really fast. Capacitive divider. You will see that this node Y is going to go to a transition. It's going to shoot up. But then, obviously, because it's a static node, the voltage source here will put it back to its original value. But what you get is something like this. It's depending upon the resistance, RS, the resistance of the source end. It could go really sharp and then gradually go down, or depending upon the resistance that I have at the node, you can basically have something which is smaller and smaller. So what you have to make sure is that the time constant of this network here is small. If that's small, then it goes quite rapidly back to original value. And the overshoot, or the coupling, will be smaller. So this case is not as bad as what we had for the dynamic node, right? This is not fatal, but it definitely could impact performance. It could create glitches. It might drive the other node to some other state, the next node to some other state, and so on and so forth. So also in this case, crosstalk could be fatal, and we have to make sure that we keep it small. The problem with this thing is that it really depends upon the timing of different signals with respect to each other. Right? If this thing happens when nothing is happening at all in my circuit, I don't care. But if I'm just doing another transition at the same time, it's going to impact my propagation delay. So you can see that propagation delay now becomes a function of what's happening in the neighborhood. Right? It's like me, I'm trying to do something, and I want to do it fast, but because somewhere my neighbor does something at the same time, it's going to slow me down. That's kind of the effects you start seeing. And that's not trivial, because from a netlist, you just look at your SPICE netlist, you won't see it. It's only when you have done the layout and extracted all the capacitance from the layout that you know that there's a problem here. Okay? So that's why crosstalk is a concern. Well, people are worried about it. And there's a lot of tools now extracting those cross-wire capacitances, and we're going to do simulation after we've done extraction to make sure that we don't have a problem with this. If you're really worried, there's some things you could do, though. And here's some examples of what I can do. Rules of thumb. Number one, if you really want to be very safe, what you do is avoid floating nodes. No dynamic logic. Right? Dynamic logic, as I mentioned, it's fast, but it's also something that makes you age a lot faster. So, problem. Number two, if you know that a node is sensitive, a node which is high impedance, a memory node or something like that, what you could do is make it somewhat protected. And protection means that you don't put other wires around it. Sometimes I might even use shielding around it, which means I might put a ground ring around it in such a way that if I have, let's say, a wire, and I put ground rings on ground wires on both sides, any wire on the other side is not going to impact it. So all my capacitance now turns into capacitance to ground. That's what shielding does. You basically create like a ground field around it, and you make sure there's no node-to-node capacitance. It's only capacitance to ground. Okay? That's what we call shielding wires. We can also use shielding layers between layers, very often done in boards, right? Any of you have ever done a high-performance PCB board, you'll notice that but definitely when you do RF or very high-speed digital, what people do is they create a full metal plane, copper, and then you have another plane with signals, then another complete plane completely filled up with VDD, then again signals, then again a ground layer. So they kind of sandwich ground and VDD layers between the signal layers, which means there's never going to be any signal capacitance that goes from signal to signal in the vertical direction. That's what's called the shielding layer. But you can do wires, shielding layers, all of this work. Obviously, this is another one, but it sounds like contradictory. But if you don't have to, don't make your rise times and fall times too fast. When they're fast, they can cause problems. So if you can be relaxed, relax. Don't push it. That's kind of the mindset here. Another one which is very interesting is differential signaling. It's an interesting one. If I remember complementary logic, right, 0 and 1, if I now have a 0 and 1 signal, and I get another signal going over it, that other signal basically becomes a common mode. It kind of cancels out. So the advantage of differential signaling is that I sometimes can cancel out interference signals. because they appear at the same way to both ends, and I drive this into the gate, it cancels out. I don't care. It moves both of them in the same way, up or down. So differential signaling is something that is attractive. And that's another one here. Even though it looks nice from a layout perspective, I'm saying, okay, I'm going to do a very nice job and start wire, 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 and I run them for millimeters together. It's easy routing, right? It's straight wires. Bad idea. If this would be a bus and I go for 1 centimeters with all my wires in my bus running parallel of interconnect capacity between those. So it means that one signal in the wire might change, and in fact what's going to happen in the other wire next to it. Bad idea. So typically what we do is going to scramble it a bit. Not having them nicely going straight and all parallel with each other. No, you kind of occasionally twist and torque them a little bit. And this way you kind of cancel out some of those effects. Okay? So many things you can do to basically deal with this wiring effect, but you have to be important. You have to be aware of it. I already talked about this one here before, I think last lecture, or 2 lectures ago, that it not only impacts the robustness, but it also impacts the performance. Obviously, as I showed you before, suppose I have 3 drivers here, a bus, 3 wires, with a certain serious kind of cross-coupling capacity between them. Now you can see that the delay of this guy here is going to be a function of what's going to happen at the neighboring wires. If all wires go simultaneously up, this capacitance totally disappears. If they also go simultaneously down, this capacitance disappears. However, if the middle one goes up and the 2 one on the other side goes down, you actually get a quadrupling of the capacitance because you get Miller effect. One goes up, the other one goes down. So we see 2 cc on one side, 2 cc on the other side, 4 cc is capacitance. If, on the other hand, my 2 extreme ones don't move, and I only move this capacitance, I'm going to see 2 cc plus my capacitance to ground, obviously. So you can see that the capacitance that I observe on this wire is going to be a function of the neighboring signals. It's a real pain, because it's something you cannot analyze statically. It's not something you can do at design time. You have to know how the signals change with respect to each other. Okay, so that's something that people worry a lot about, is the fact that you have those dynamic cross-coupling effects. And this is showing basically a factor of, this is the same thing, you get to 1 plus 4R to OR. So big differentiation in delay is possible. So one way to get around some of these things. So we can do these tricks from a design perspective. You can try to isolate wires out. You can try to do another thing. The other one would basically say, well, gee, if I would just keep the capacitance small, wouldn't that be nice? So you probably have heard about this. It's what people use today in most advanced processes. You do 95 nanometers, 65 nanometers, all this type of processes. Today, they all use what we call a low-K dielectric. You change epsilon. If the capacitance is equal to epsilon over T, and I make epsilon smaller, I get smaller capacitance. Cool. Right? So we go away from silicon dioxide. That's what you typically used to do. Today we're using basically organic materials, polymer-based type of polyamides. And some people are really playing around with aerogels. Aerogels are kind of a gel with bubbles in. So you have kind of air, but not completely air. But it's almost like the epsilon of air, which is way better than what you would get, for instance, with silicon dioxide. Okay? So reducing epsilon is something that our technologists are trying to do extensively, and has been used effectively now in all processes. Like we increase the epsilon for the gate material, there you want to get a thinner gate with higher dielectrical. You want to get a higher dielectrical component for a better transistor. For the interconnect, we do the opposite. We use low-K dielectrics. Okay. Okay, I showed this capacitive crosstalk, shielding. Right, this is the shielding idea. You either put neighboring wires that are connected. Here you have wire. You put a ground wire in between. No problem. Or I put a VDD plane below it. There's no coupling anymore between the wires on top of each other. That's what I mentioned. It's basically shielding. Again, this is something that designers of very high-speed logic have done for ages. People building really, really, really fast stuff. Either boards for, let's say, supercomputing, memory boards, all those kind of things. That's what they do. Okay. Now, suppose now that you're asked to design a very, let's say, a bus on a chip. These are, if I think about on a chip, what are the largest capacitance signals? It's obviously the clock, number one, and then it's buses. Why are buses a problem? Well, a bus is something that's going to basically run over the chip and connects a whole bunch of units together. Right? It goes from the CPU to the memory arrays, it goes to the I/O units, the timers, the peripheral devices. So you have wires basically that have a whole bunch of things connecting to them. And they go everywhere. So they're long and they have a lot of fan out. So typically you can see capacitance here to 2 picofarad, 4 picofarad, or something like that. So now, what can I do to make this thing fast? Right, so you have a big, big, big capacitance. How do I drive it fast? Well, we know the answer, right? Obviously, if you look at the propagation delay, CL is given. I average is determined by the last stage, and V swing. So there's two options that you can play around with. Option number one is transistor sizing and cascading buffers. Right, we know that. If you basically make those drivers a lot bigger, we make very big transistors. You use cascaded inverters. Go for a long chain of those type of things. We can drive this thing fast. Well, fast is still not the right word. We can optimize the delay of the driving. And we know what the absolute minimum is going to be. So that's one option. Transistor sizing, cascading buffers. Very often used, you look at any chip, you will see these large chains of inverters. Definitely when you go off chip. The other option that you might consider in certain cases is the other thing, is V-swing. Right? If I have a long wire, and I want to drive it fast with fairly small amount of power. Because remember, if I cascade buffers, you have big transistors, you have a lot of inverters in a row, it's a lot of area and a lot of power. Because the driver itself, you're not only switching this capacitance around, up and down, but also all those inverters that are sitting in front of it. All the capacitance of those devices is going to go up and down, which could be about 40% of the total capacitance. So a better way to say, well, maybe what I should do is instead of driving the signal all the way from 0 to VDD, I'm maybe just going to make it swing for a little bit, maybe 100 millivolt only. So I have a driver, a transmitter we call it in that case, where you apply your input waveform. So you have a little thing here. You apply your input waveform, and at the output is only a tiny little signal, say 100 millivolt. That propagates to the wire. Again, you're going to optimize the wire and how you drive and all those kind of things. But the advantage now is that I don't have to basically use that much charge. I'm only going to have QV is going to be a lot smaller. Q is going to be a lot smaller in this case. So it can be faster. And the other advantage from a power perspective, now my capacitor is only going to swing from 0 to delta V. So my power dissipation is going to be C times, or my energy is going to be C times VDD times delta V. So you get a linear reduction in power dissipation. Okay? Now the problem obviously on the receiving side, you get this tiny little signal. What do you do with that? Well, you have to amplify it again. So the first thing this is going to go into is an amplifier stage. That brings it back to the full swing. This we call a receiver. This is a transmitter. It's a receiver. You make it a communication channel. Right? It's power effective, and it's potentially very fast. But it's tricky. It's analog design. When I mention the word amplifier, we basically think right away analog. Right? So you have to be a lot more careful in biasing, offsets, and all those kind of things that you play around with. Now, one place where this is used most often, in virtually every memory chip that you're basically going to use, this is what we're going to do. Not in SRAM, but definitely DRAM. You look at the dynamic RAM. What you have is a whole bunch of memory cells connecting to the output. So I want to read it out. So you have a large column of memory cells, and you want to read these things out fast. Okay? There's one little wire coming out. This is called the bit line. Huge capacitance, driven by a tiny little memory cell. As the memory cell has to move that bit line up and down. I'm a 0, I'm a 1. I'm a 0, I'm a 1. So you have small transistors trying to change a big capacitance. The only way to do that is by, well, we're not going to change that bit line very much. We apply the cell to it, and it's going to kind of wiggle it a little bit up, a little bit down. And then at the end of the wire, we put an amplifier, which we call a sense amplifier. And the sense amplifier is going to measure that signal and amplify it all the way back to 0 and VDD. So memories use this technique of reduced swing very extensively. But again, this is only in areas where you have very tight control over the noise, interference signals, and all this type of thing. And memory, you can do that because it's very regular. In logic, it's very scary. Okay, we've done it. I've done dynamic buses. I've done reduced swing buses and all this kind of thing. It works, but it takes a lot of attention. Okay, so getting back to the cascaded buffers, we know how this basically plays. We talked about this number many times. But be aware that if I have to drive, let's say, 20 picofarad, I have to go off chip. So I have a package, chip package, pins coming out, sitting on a board, traces on the board, some other components connect to it. You can easily count that the total capacity that this pin, or that the driver that has to drive that pin is going to see is about 20 picofarad. That's huge compared to your 65 nanometer or 90 nanometer device, which has a capacitance of a couple of femtofarad. So we have a ratio of 1,000 to 10,000 in capacitance ratio, input capacitance, drive capacitance. Now, if you start working that out, and you figure out how many stages you need, you see that you're easily going to need 6, 7, 8 stages of inverters. And more importantly, that the transistors that are going to be sitting at the end here is going to be humongous. Huge transistors, not resistors, small resistors. Because obviously we're going to have to drive those things. So yes, you can use all the techniques we have discussed in class. You can find the optimal design for this thing. But I can guarantee you it's going to be a power hub. It's really going to be huge transistors, lots. It's going to be a huge area as well, a lot of chip area. So again, in this case, the normal standard rule we have basically given so many times basically still applies. And the rule basically says the following thing is back off. If you don't have to be too fast, slow down a little bit, and it's going to save you a lot. Make your buffer 5% slower. Change the rise and fall times a little bit at the output. It looks like you're giving up a little bit, but 5%, who cares? But the win is going to be 40, 50, 60% in power dissipation. So backing off a little bit from the extreme is always a good idea. And I think I can show this with this example here. You can find actually the area and the energy it takes to drive. We discussed this before. If you know the optimal solution, you can find the optimal number of stages, you do optimal fan-out factor, you plug it in, you can figure out how much extra energy the buffers are going to take, how much area they're going to take as well. So for 10,000, if I have a fan-out of 10,000, I'm going to need about 7 to 9 buffer stages approximately, in the ideal case. However, if I back off a bit, and this is for a 0.25 micron process. So think about this. Ideal buffer, propagation delay 0.76 nanoseconds, load capacitance 20 picofarad. I need transistors in the 7th stage, which are 1.5 millimeter long. Now, think about it, right? That's a huge white transistor, 1.5 millimeter. These are transistors you can see with the bare eye. You look at the chip and say, oh, there's a big transistor out there. Most of the time, we don't see anything else than metal and a lot of stuff. For the NMOS, about 0.8 millimeters. These are humongous transistors. And you can imagine the power dissipation of those things is not going to be low either. While if I just say, okay, I double the delay, this is not 10% or something, let's just double it. Instead of now I only need 3 stages, and you see that the largest transistor I'm going to have is only about 0.3, 300 nanometers approximately. 300 micron approximately. So a lot better in overall perspective. So you have to be very careful here. Driving things for optimal speed can really shock you and become very expensive. This is an example of such a thing. As I mentioned, driving on a chip, the places where we see the biggest capacitances are going to be the clock, buses, and the third one is I/O. Every time I have to go off chip, we have to provide a connection to the outside world. And you've probably seen pictures of chips before, how you do that. That's you put the silicon down and you make nice little bonding wires, gold or copper, whatever, and you connect it to the substrate. Right? In order to connect to the chip, to the silicon, we need a connection area. We call this the bonding path. The bonding path is a piece of metal. Used to be 100 micron. Nowadays, with more advanced technology, it's gone down to 50 micron approximately. The tools have gotten better. Because now you have to watch out, right? I have to be able, mechanically, put down a blob of solder type of material, and then connect the wire to this. So if you make it too small, it's going to be very hard to get that wire to connect to it. So this is a blob of metal. The way you connect to it is, it's the way, if you look at your chip, you have all your metal stuff here. So assume that this is one of those paths. Typically, the last thing we're going to do in a normal chip processing step is we're going to cover everything with silicon dioxide. They call it glass. It's transparent material. Basically, it's something that you're done. You have done all your metal layers, and then you're going to protect the whole thing by putting a chunk of silicon dioxide over it, just to make sure that the chip doesn't get damaged too easily. It's a protection layer. But obviously, to connect to your pads, you have to make holes in this. So you etch those holes to this overglass so that I can connect to this metal pad, and then I can basically have this wire coming out of this. Okay? That's called a bonding wire, or wire bonding. So we have this thing, but remember now, of this hangs a inductor. That's this wire is an inductor. And all this capacitance of the board, the pin of the chip, all the fan-out stuff, that's the 20 picofarad thing here. So driving that 20 picofarad at a certain speed is important, and that's where you're going to need those cascaded buffers again. And the last stages are going to be this huge transistor, and you can really recognize this is 100 micron. This is an NMOS transistor, and this is a PMOS transistor. And actually, in order to make them more effective from a layout perspective, we're going to use one very wide, very skinny transistor. That would not be a very good idea. So what we more generally do is create them as a set of parallel transistor, where you have, you put diffusion down, and you have source, drain, source, drain, source, drain, source, drain, and you use metal to connect them to each other. So it's like a whole chain of parallel transistors you're putting next to each other. It's a much more effective approach. It also makes sure that your polysilicon strips, the ones that go basically creating the gate material, are not too long. Otherwise, you would have too large a resistance. You don't want to have that either. So this is an art. Designing those bonding paths is not easy. Making them effective, making sure that they work. So that's the first thing you always go. When you go to a fab and you ask for a library of cells, you better make sure there's basically bonding paths included in that library. Because that's a crafty design. And you can have latch-up problems there. There's a whole bunch of other things that might emerge. Another thing that might emerge is around there, something that people are concerned about is what's called ESD protection. I'm not going to say very much about it because you can talk a long time about this. But ESD, ever heard about ESD? Electrostatic protection. It's the fact that if I'm as a human, when I rock around on carpets, I'm basically a floating body, and I charge. Because of basically friction, you charge up. And it's not uncommon that we have charges or voltage on our body of about 10,000 volts. And then you touch the doorknob and you see these sparks flying, right? Now, suppose now that you as a human, or whatever it is, you take a chip and you're there coming in, let's say an input pin. So your input signal, input pin goes in, goes to and connects to a gate of a transistor, right, of an inverter, let's say. Right away you do some buffering. The thickness of those gate oxides, remember, nanometers. There you are. You take that pin in your hand with your 10,000 volts. You apply it, you blow right away that gate capacitance away. You just zap it. The chip is gone. So this is, it happens all the time. People say, oh, nah, I'm going to be careful. Now, first thing they do, they touch the thing, blow it up. So that's why most people working on pins, chips, soldering them down, are going to ground themselves first. You're basically going to put a ground pad around you, and you make sure that you're at the same voltage, ground voltage, as the board you're working on. But the second thing we're going to do is ensure that on the chip itself, we provide some bypass paths for these big currents to flow. Just like in a diode. You just, at the input pad, you put some diodes in such a way that you create an overvoltage, 10,000 volt, you right away turn on the diode, and all the current goes to the diode, except and not going to the capacitor that sits at your input gate. So ESD protection is very important, and that's an integral part of any I/O pad. So it's the bonding pad, you have the output buffers, and you have all this ESD protection stuff, which makes it really hard. And it's not getting easier, because your capacitor is getting smaller and smaller and smaller. Your oxides are getting smaller. So making sure that those currents don't do any harm is quite essential. So this is kind of the way it's typically done. So if you're a path, here's your little inverter. As I said, basically what you see is here is this gate capacitance. I come in here and I apply 10 kilovolt. Not for a very long time, but you can imagine I apply 10 kilovolt over this oxide here. The ground's here, 10 kilovolt here, it's gone. Right? It's basically you blow away the whole capacitor. So the way to do that is by adding some resistance to it. Yeah, it's going to slow it down a little bit. You have to be very careful because it slows down your input signal. And 2 diodes, one to ground, one to VDD. Now, if I go to 10,000 volt, what's going to happen is I'm going to turn on this diode, and all my current is going to flow instantaneously into the VDD rail and shield it away. So the voltage here will never develop. It will go to VDD plus the diode voltage. Okay? So that's really what the ESD protection is all about. It's making sure you add some resistors here and there and add some diodes there as well. And you can actually see in this layout where they're basically sitting. Here's the pads. And we see so I have some big diodes that are designed right into it. Okay? So tricky. This is what I would say almost, when you really get to become a professional designer, that's kind of stuff you're going to play around with. But you try to avoid it because you don't do this thing too often. You do it one time for technology generation, you reuse the pads over and over and over again. Okay, all this kind of shows a little bit what we were all talking about when I talked about this bonding wiring and so on and so forth. Somebody has a message here. So, suppose I have a package. The way we just putting it all in perspective, here's my chip. The chip is bare silicon. It's been cut out from the wafer. You take the wafer, get it back, you slice it all into pieces, and you get these chunks of a couple of square millimeters. The package itself is a substrate. Typically, it's a conducting substrate, and that's where you're going to provide the ground signal. The ground basically is all going to be grounded. It's conductive glue. We glue the silicon on top of it. And then, so you have your silicon sitting here. Now I have to connect it to those pins. Nowadays, they don't look like that anymore. They're more like bumps. Because if I have to put 1,000 of those together, it's not as easy. But let's say you have a pin. What I have to make sure is that I make a connection to this trace on the substrate and the path on the chip. And that's where this wire bonding comes in. This is done automatically. Because if you would have to do this by hand, now you have 50 micron movement space. And some of the modern processors is hundreds of pins to 1,000 pins. were to do all this by hand, it would be, those machines are extremely fast. You see them in action, it's quite incredible. They go in and they make all the connections in about no time. Pretty incredible technology. But you can see that the trace now going over the chip is not as trivial. So you have all those very fancy closed, very optimized transistors, very close to each other. And now you see this big wire coming out, inductor. You have this trace, and you have another pin here. This is then glued together. We have solder sitting here, all those things creating capacitance, and so on and so forth. So pretty challenging. So that's why people nowadays try to do more and more. That's why, reason one, we try to put as much as possible on a single chip. Because if you have to have 5 packages, you have to go off from package to the pins, back on the board, going back out. If I can put the memory on the same chip, it's a lot better. Right? It can be faster. You don't have all this extra inductance, all this extra capacitance at all. So that's one. Another thing that what people do about it is either, number one, more integration. Right? That's the nice thing about having 1 billion transistors on a chip. I can put the core memory and the processor and the cache memory and all this kind of stuff on the same die. Or I can put 16 processors on a die. If you cannot do that, the second thing what people very often do is system in a package. You actually put multiple of the silicon dies on the same substrate. And you connect them together with wires, bonding wires like this, in the same package. You might not see that. You might get a microprocessor chip and you think it's only one chip because you see only one single package, but it might be 2 or 3 chips in there. Today with memory, very often done. If you want to get a bigger memory, you put a couple of those memory things together. And today people are now trying to get rid of those packages altogether, stacking more and more silicon die on top of each other, connecting them vertically and all this kind of fun stuff, and then finally put them all together into one single package. So this is called 2.5D or 3D integration. It's becoming more and more popular in the industry. Trying to jam as much as possible together, but not making your chips bigger, because that's sometimes hard, but actually having different chips and kind of put them very tightly together to reduce the parasitics. Okay? So very important thing to think about. We often forget about it. Right? We're designers. We think about, oh, my goodness, are we going to design buffers? We're going to design adders and memories and all these kind of things. But actually, the package, thinking very carefully on how to partition the system, can save you a lot more than basically optimizing your little buffer a little bit better or something like that. So there's some very important decisions, some very high impact design things to be done at this level. And as I said, it's getting a lot more popular these days. Everybody in the industry is talking about this 3D, 2.5D, or system and package type of integration. Okay? So tomorrow we'll talk about clocks and power distribution. Okay? All right. See you then.